In earlier lessons, we solved the Schrödinger equation for the particle in a one-dimensional box and examined the solutions. In this lesson, we will look at what happens if we allow the particle to move in 2 dimensions, then in 3 dimensions. Let's start with the 2-dimensional problem. Now we need 2 coordinates, x and y, to specify the location of the particle. We will confine our particle to x coordinates between x equals 0 and x equals L1, and y coordinates between y equals 0 and y equals L2. So we have a rectangular box. Just like the one-dimensional case, we will examine the case where the potential energy is 0 inside the box and infinite outside. In this case, the time-independent Schrödinger equation is h hat psi equals E times psi, where the Hamiltonian operator consists of a kinetic energy operator to account for motion along the x-axis, negative h bar squared over 2m times the second partial derivative with respect to x, and a kinetic energy operator to account for motion along the y-axis, negative h bar squared over 2m times the second partial derivative with respect to y, and a potential energy operator, which we don't need to write here if we define it to be 0. Note that the wave function now depends on 2 variables, x and y. We are going to use a technique called separation of variables to solve our 2-dimensional Schrödinger equation. There is a theorem that says that if an operator is a sum of operators that affect different variables, then it is possible to find eigenfunction that is a product of functions that each depend on only one of the variables. Let's illustrate by applying it to our current problem. If we examine our Hamiltonian, we can see that this part only affects the variable x. Let's call it operator t sub x. And this part only affects variable y. Let's call it operator t sub y. So our Hamiltonian here is an operator that is a sum of 2 operators, with each of the operators depending on a different variable. What the theorem is saying then is that we can find an eigenfunction that can be written as a function of x times a function of y. Here we're using uppercase x as a symbol for our function of x and uppercase y as our symbol for the function of y. Remember, lowercase x and y represent the coordinates of the particle. Here's the proof. We start with our 2-dimensional Schrödinger equation, h hat psi equals E times psi. For h hat psi, we substitute t sub x hat plus t sub y hat for h hat, and substitute the product of functions x and y for psi. The rule for sum of operators says that we can apply each operator separately, then add the results. Let's take a look at the first term here. We know t sub x hat only affects variable x. As far as this operator is concerned, function y is a constant. So, since the operator is linear, we can pull out y, and this becomes function y times t sub x hat applied on function x. Similarly, t sub y hat applied on function xy gives us function x times t sub y hat applied on function y. Of course, E times psi is just E times function xy. So after doing the substitutions, h hat psi equals E psi becomes y times t sub x hat x plus x times t sub y hat y equals E times xy. Dividing both sides by xy, we get t sub x hat x over x plus t sub y hat y over y equals E. We rearrange this equation so everything that depends on the x-coordinate is on one side and everything that depends on the y-coordinate is on the other side. If 2 sides of an equation are expressions that depend on different variables, then both expressions must evaluate to a constant. For obvious reasons that will become obvious, let's call that constant E sub x. So the left-hand side becomes t sub x hat x over x equals E sub x. and the right-hand side becomes E minus T sub y hat y over y is also equal to E sub x. So now we have a fairly simple problem to determine the function of x. We can rearrange the equation to get T sub x hat applied on function of x equals a constant E sub x times function of x. Similarly, determining the function of y is simple. We can rearrange this equation to get T sub y hat y over y equals E minus E sub x. But E minus E sub x is just a constant, minus a constant, so it's just another constant. We can just give the constant another name. Let's call it E sub y. It should be easy to see that our y problem can now be rewritten as T sub y hat applied on function of y equals E sub y times function of y. We did not encounter a contradiction, so our assumption is valid. Note that we simplified our two-dimensional eigenvalue problem into two one-dimensional eigenvalue problems, which are much easier to solve. In fact, we have already solved these one-dimensional problems. Note that we simply add the eigenvalues of the two one-dimensional problems to get the eigenvalue for the two-dimensional problem. In other words, the total energy E is just equal to E sub x plus E sub y. Okay, let's recap what we've done so far. We wanted to solve the Schrödinger equation which had two independent variables x and y. It so happens that the Hamiltonian can be written as a sum of two operators, one depending only on x, the other depending only on y. We've proven that there are solutions that can be written as a function of x times a function of y. To determine these solutions, we solve two simpler eigenvalue problems, one depending on x, the other one depending on y. And the sum of the eigenvalues of the two simpler equations is equal to the energy of the system. Now let's take a look at the simpler equation that only involves x. The T sub x hat operator is just the kinetic energy operator for motion along the x-axis, and it is negative h bar squared times the second derivative with respect to x. If we look closely at this problem, we'll notice that we've seen this before. It is essentially the one-dimensional particle in a box problem. So we already know the solution. We just need to match the symbols we use for the one-dimensional problem with the symbols we are using here. What we call psi is now big X. What we called E is now E sub x. Instead of L for the length of the one-dimensional box, we now use L1, which is the length of the rectangular box along the x-axis. And the quantum number n for the one-dimensional solution, we now call it n sub x. So we have big X is equal to square root of 2 over L1 times the sine of n sub x, pi x over L1, and E sub x is n sub x squared times h squared over 8m L1 squared. Similarly, we can solve for the part of the wave function that depends only on the y-coordinate, and it is equal to square root of 2 over L2 times sine of n sub y pi y over L2. The eigenvalue E sub y is n sub y squared times h bar squared over 8ml squared. Here, L2 is the length of the rectangular box along the y-axis, and n sub y is another quantum number with similar restrictions as n sub x. Now we have the complete solution. The wave function psi is equal to the product of a part that depends on the x-coordinate and a part that depends on the y-coordinate. The total energy is the sum of E sub x and E sub y. Recall that to describe the particle in a one-dimensional box, we need to specify one quantum number n. We can see here that for the two-dimensional box, we now need to specify two quantum numbers, n sub x and n sub y. This is a pattern that we will observe in 3 dimensions, we will need 3 quantum numbers. We can easily extend the solution to 3 dimensions. This time, the Hamiltonian can be written as a sum of 3 kinetic energy operators, with a third depending only on the z coordinate. So, the solution psi is now a function of 3 variables, x, y, and z. And it can be written as a product of a function that depends only on x, a function that depends only on y, and a function that depends only on z. And we can split our overall problem into 3 one-dimensional problems to solve for each of these 3 functions. The parts that depend on x and y are the same as what we saw for the 2-dimensional problem. The part that depends on z is essentially the same form. It's square root of 2 over L3 times sine of n sub z pi z over L3 with eigenvalue e sub z equal to n sub z squared times h squared over 8m L3 squared. Here, L3 is the length of the box along the z-axis. And n sub z is another quantum number with similar restrictions as n sub x and n sub y. The total energy of the particle is just the sum of the eigenvalues e sub x, e sub y, and e sub z. Let's take a look at what plots of psi would look like for a particle in a 2-dimensional box. We will need 3 dimensions to create this plot since our function psi depends on 2 variables, x and y. Let's draw the axes for our independent variables. Here's the x-axis, here's the y-axis. The third axis will be for our dependent variable, which is psi. If psi is positive, you can imagine the point representing it as sticking out towards you, and the point for a negative psi value will be sticking out away from you. Let's say this is our box. Let's take a look at how we would plot this specific function. Here's the part that depends on x. We can easily identify a here as the length of the box along the x-axis. It's what we called L1 earlier. We can also identify 3 here as the quantum number n sub x. This means we expect to find 2 nodes along the x-axis. Remember that the number of nodes is n minus 1, and they are evenly spaced. So we expect the 2 nodes along the x-axis to be at L1 over 3, or a over 3, and at 2/3 of L1, or at 2a over 3. Here's the part that depends on y. We can easily identify b here as the length of the box along the y-axis. It's what we called L2 earlier. We can also identify 2 here as the quantum number n sub y. This means we expect to find 1 node along the y-axis. We expect that node to be halfway through the length of the box along the y-axis. So we expect to find it at y equals b over 2. Now, let's see what the algebraic signs are for our wave function. We know the function changes algebraic sign as we go through nodes. We know that the part that depends on x is positive before the first node on the x-axis, negative after the first node, then positive again after the second node. We know that the part that depends on y is positive before the node on the y-axis, then negative after that node. What we've done is divided the box into sections based on the location of the nodes. Let's look at this section from x equals 0 to a over 3 and from y equals 0 to b over 2. The part that depends on x is positive here, and so is the part that depends on y. The product of 2 positive numbers is positive, so we expect the wave function psi to be positive in this section. What about this next section? Do we expect psi to be positive or negative? Since we go through a node in going from one section to the next, we expect psi to change algebraic sign. So, psi should have opposite algebraic signs in neighboring sections. It will be negative here. It should be fairly straightforward to deduce that psi is positive here, negative here, positive here, and negative here. Here's a 3-dimensional plot of psi versus x and y for n sub x equals 3 and n sub y equals 2. Here's the x-axis. The length of the box along the x-axis is A. Here's the y-axis. The length of the box along the y-axis is B. Remember that the nodes divide the box into sections, in this case, 6 sections. Here's a way to visualize psi in the 6 sections of the box. There are 3 mountains and there are 3 trenches. If one section has a mountain, then the next section has a trench. The peaks of the mountains are shown here in red. The bottoms of the trenches are shown in blue. This is the peak in the section between x equals 0 and the first node at x equals a over 3, and between y equals 0 and the first node at y equals b over 2. Here's a three-dimensional plot of the probability density function for the wave function we just saw earlier. Remember that the probability density function is the square of the absolute value of the wave function. Now, instead of 3 mountains and 3 trenches, we see 6 mountains. What we drew as trenches are now drawn as mountains since the square of a negative number is positive. Here's another way of plotting the wave function for a particle in a two-dimensional box. We can use contour plots. A contour is just a curve that traces through all points with the same value of psi. Imagine a contour as a curve that represents points on a mountain that are at the same elevation. Take a look at this section, which represents this mountain. Let's zoom in on the contour plot. You can see that the innermost contour is labeled 0.8. That means the value of psi at the points on the curve are 80% of the maximum possible value of psi. That corresponds to this elevation on the mountain. This contour labeled 0.4 represents locations where the value of psi is 40% of the maximum possible value of psi. This corresponds to this elevation on the mountain. Plots for the particle in a three-dimensional box are much more challenging to create, but can be done with modern computer software. It's more challenging because you need 4 dimensions, x, y, z, and either the wave function or the probability density function. A typical way of plotting the probability density function is to represent it by a cloud, as in the example shown below. The cloud is thicker in regions where the square of the absolute value of psi is larger. You may also use different colors to differentiate clouds where the wave function has opposite algebraic sign. It's not done in the example shown here. In the example shown here, the quantum numbers for the wave function are 2, 3, and 2 for n sub x, n sub y, and n sub z, respectively. Here's the x-axis, here's the y-axis, and here's the z-axis. Since n sub x is 2, there is one node along the x-axis at x equals L1 over 2. That's a plane that is parallel to the yz plane. The plane divides the box into 2 sections. With n sub y equal to 3, we expect 2 nodes along the y-axis at y equals L2 over 3 and 2L2 over 3. These are planes parallel to the xz plane. These planes divide the box into 3 sections. With n sub z equal to 2, there is also one node along the z-axis at z equals L3 over 2. This is a plane parallel to the xy plane. This plane divides the box into 2 sections. Altogether, the nodes separate the box into 12 sections, and the probability density is a maximum in the center of each of these 12 sections. This rectangle connects the centers of the 6 sections between the nodal plane at x equals L1 over 2 and the face of the box parallel to the yz plane. This rectangle connects the centers of the 4 sections between the nodal plane at y equals 2L2 over 3 and the face of the box parallel to the xz plane. This rectangle connects the centers of the 6 sections between the nodal plane at z equals L3 over 2 and the face of the box parallel to the xy plane. We have seen that the energy of the particle in a rectangular box is equal to E sub x plus E sub y, where E sub x is n sub x squared times h squared over 8m L1 squared, if L1 is the length of the box along the x-axis, and the quantum number n sub x is restricted to non-zero integers. Similarly, E sub y is n sub y squared times h squared over 8m L2 squared if L2 is the length of the box along the y-axis, and the quantum number n sub y is restricted just like n sub x. What is the lowest possible value of E sub x? That would be when n sub x is equal to 1. Let's call that E sub x1. What's the lowest possible value for E sub y? That would be when n sub y is equal to 1. Let's call that E sub y1. What is the ground state energy for the particle? That would be the lowest possible energy, which would correspond to n sub x equal to 1 and n sub y equal to 1. So that would be E sub x1 plus E sub y1. The first excited state is the lowest possible energy. That would mean that one of the two quantum numbers is 1 and the other is 2. That means either E sub x1 plus 4 times E sub y1, if n sub y is 2, or 4 times E sub x1 plus E sub y1 if n sub x is 2. What is the first excited state if L1 is longer than L2? Well, if the L in the denominator for E sub x1 is larger, it would mean that E sub x1 is smaller than E sub y1. An increase in n sub x will cause a smaller increase in the total energy compared to the same increase in n sub y. Therefore, the first excited state, if L1 is longer than L2, would correspond to n sub x equals 2, which means E sub x is 2 squared times E sub x1, or 4 times E sub x1. The first excited state energy is 4 E sub x1 plus E sub y1. However, if L1 is less than L2, then the first excited state energy is E sub x1 plus 4 times E sub y1. We can see that, in general, stationary states of a particle in a rectangular box are non-degenerate. We say in general because, as we are about to see, if the box is a square, we will see degeneracy. Here's what happens if the box is a square. E sub x is n sub x squared times h squared over 8ml squared, and E sub y is n sub y squared times h squared over 8ml squared. Note that L1 and L2 are equal for a square, and we can just use the same symbol for both. In this case, we just represent both by L. The lowest possible value for both E sub x and E sub y will be the same. When n sub x is equal to 1 or n sub y equals 1, then E sub x or E sub y will just be h squared over 8ml squared. Let's just call this E sub 1. It should be easy to show that the energy, which is E sub x plus E sub y, is just equal to n sub x squared plus n sub y squared times E sub 1. The ground state, as before, is when n sub x and n sub y are both equal to 1. That corresponds to 2 times E sub 1. The first excited energy level is when one of the two quantum numbers is 2 and the other is 1. Regardless of which quantum number is 2, the energy is the same. 1 squared plus 2 squared is 5. The energy is 5 E sub 1. We say that the first excited energy level is doubly degenerate, or that the degeneracy of this level is 2. What we mean when we say that the degeneracy of an energy level is 2 is that there are two possible quantum states that would have this energy. Going back to the ground energy level, we describe the level as non-degenerate or singly degenerate. We say that the degeneracy of the level is 1. The second excited energy level should be when both quantum numbers are equal to 2. 2 squared plus 2 squared equals 8. So the energy of the particle would be 8 times e sub 1. And we can see that this level is non-degenerate. The pattern should be obvious by now. When the quantum numbers are the same, the degeneracy is 1. Otherwise, it's 2. Degeneracy is something that arises due to symmetry. A rectangle is more symmetrical if it is a square. For a particle in a three-dimensional box, we expect that, in general, the energy levels will be non-degenerate. However, if we have a cubic box, then we would expect to see degeneracy. The energy for a cubic box will be the sum of E sub x, E sub y, and E sub z, where we use the same length in the formulas for all three. The lowest possible value will be the same for E sub x, E sub y, and E sub z. That would be when the corresponding quantum number is 1. Let's call this lowest possible value E sub 1, which is h squared over 8ml squared, or h squared over 8mv to the power 2 over 3, where v is the volume. Since the volume of a cube is L cubed, we can also say that L squared is equal to volume raised to the power 2/3. It should be easy to show that the energy of the particle is just E sub 1 times the sum of n sub x squared, n sub y squared, and n sub z squared. Therefore, the ground energy level will be the case where all three quantum numbers are equal to 1. 1 squared plus 1 squared plus 1 squared is 3. So the ground energy is 3 times E sub 1. We get the first excited energy level when one of the three quantum numbers is 2. 1 squared plus 1 squared plus 2 squared is 6. So the first excited energy level is 6 times E sub 1. There are three ways that this can happen. Either n sub z is 2, n sub y is 2, or n sub x is 2, while the other two quantum numbers are 1. So what is the degeneracy of the first excited energy level? The answer is 3. The level is said to be triply degenerate.